All right. So always start by plotting the original, just so you get an idea of what's going on. All right, so u is at -2, -4. There we go. So u is at -2, -4. Here. -4, 0 is v. -1, 1 is w. And 3, -2 is x. So this is what my figure looks like originally. And make sure you label it so that you know which point's which. Now, we're going 90 degrees counterclockwise. So, if let's say I was starting at the first quadrant, would I be going to the left or to the right for counterclockwise? To the left, you're going this way. All right. So, some of you guys, I think, did clockwise. I think that's where the disconnect was. All right. Now, what did I say yesterday is important with rotations? Well, so one thing that I said, if all else fails, what do you need to remember about rotations?
They're a rigid motion.
Well, yeah. But in terms of actually finding the rotation, what I say is the main key to doing rotations. So if I told you, and I told some of you guys this while I was going around the room, what did I say you would have to do with rotations in order to graph it? Or find the new points? What do? I'm not telling you, so you guys better look back at your notes. So what did I say is the key process for graphing rotations or finding the new points? Guys, your Chromebook should not be out. Make sure they're up. I'll give you a hint. Note-wise, I wrote at the top of page 15. I wrote it at the top of page 15. What did I say?
Every 90 degrees for the x and y and change the signs.
Right. Change the signs to do what?
Fit
the quadrant. So I said every 90 degrees, you flip x and y, change the signs to fit the quadrant. All right. So let's start with u. What quadrant is u in?
Negative.
What quadrant? I want the number. It's in quadrant 3. So we know that that's negative. This one's positive, negative, negative, positive. When you're doing rotations, you probably should just go ahead and write that just so you know. So, what's my first step? So in other words, if I'm rotating 90 degrees counterclockwise, if I'm in quadrant 3, where do I end up? Quadrant 4. All right. So that means my point has to look something like what? Positive, negative. So u prime, we know it to be something positive, something negative. Then what do I have to do? Not flip the signs, but flip the
X and Y.
the numbers. All right. So this becomes 4. This becomes 2. Don't worry about the negative signs currently in front of them. You only need to worry about the actual numbers themselves. Ignore the negative signs. The only thing that the negatives come into play with is it just tells you what quadrant it's currently in. All right, because remember what I said, you change the signs to fit whatever quadrant it's going to. All right, so U would be at 4, -2, so right here. That's U prime. V prime, where's it at?
Being on the Y.
So V is currently on the x-axis, so it needs to go on the y-axis. All right, 90 degrees. So if it's on an axis, it's going to the other one if you go 90 degrees. However, which side of the y-axis? Are we going on the top half or the bottom half? We're going on the bottom half. So that means that that y value has to be what?
Negative.
Negative. So we know the y value is going to have to be negative because it's going on the bottom of the y-axis. So what's the new point?
0, -4.
0, -4. So right here. W. All right, so to get W prime. First off, where's W currently located? Someone besides Ephraim or Luke or Owen?
Quadrant 2.
Quadrant 2. All right, so Kyrie's now on the list of can't talk. Where's it going?
Quadrant 3.
Quadrant 3. So now Abigail's on the list that can't talk. All right, so it's going to quadrant 3. So that means the signs have to be what?
Negative.
Negative. So that means Cohen's on the list that can't talk. And then what's the numbers look like? 1, 1. So now Carolina's on the list that can't talk. All right. So it'd be at -1, -1. So right here, that's W prime. Finally, X prime. Where's it originally?
Quadrant 4.
Quadrant 4. All right. So Michael's on the list now that can't talk. Where's it going? Quadrant 3. All right. And I didn't hear who said it. Now Anthony's on the list that can't talk. Well, no. If it's in quadrant 4, you're going backwards. You went the wrong direction. So it's going to quadrant. Quadrant 1. So what's the signs look like? Positive, positive. So that means my new point is not 3, 2. 2, 3. So it's right here. So that's what your new figure should look like. Now, if I asked you to go 180 degrees, what would have happened to the x's and y's? Specifically, what would have happened to the position of the x's and y's in relation to what we started with? So this is xy, this is yx. So what would 180 be? So I'm not worried about the signs. I'm just worried about whether we're flipping x and y or not. So if we start xy here, we go 90, that's yx. So 180 would be back to xy. 270 would be yx. All right. So we're not going to do that. I just want to make sure that you understood that. So remember, every 90 degrees, flip x and y. All right. So 180 degrees, you don't have to flip x and y because you've already gone 2 sets of 90. All right. So when you guys are doing rotations, this should be what you're asking yourself in your head. You need to ask yourself essentially the process that we just did. What quadrant is my point currently in? Where's it going to end up? So what's the signs going to look like? So what's the numbers going to look like? All right. Though that is what you should be asking in your head every time you do a rotation. All right. Does that make sense to everyone? All right. So what we're going to be doing today is we're going to finish up that last little bit of 1.4, which is the symmetry aspect. That's very, very quick. And then we're gonna move into dilation, which should be our last transformation that we're learning about. Now, before we get into it, a couple of things. So, next week, we have no clue what's gonna happen, because if you guys have seen the weather, like, we're probably most definitely getting snow,
Really,
all right?
for the whole weekend.
We don't know, all right? It's up in the air. So, what we're doing, what we want to do, because we'll basically finish the unit by tomorrow, all right? So I went ahead and gave y'all the test review just to have. So like if we do have snow, and we will not take the test the day you come back, but if we do have snow, just so you already have the review ready to go, all right? So if there is snow and we're out for a couple of days, your job is to get your journal done, work through the review, and do any delta math that you still have to do. All right? So remember, because a couple of you have asked me this question. Remember, delta maths, the way I grade them is I do the initial grade the day of the test. It's by completion, not by percentage right. So the due dates in delta math are the tentative due dates that you don't get behind. All right? So if you don't do them by the due dates, okay. All right, you got till midnight on test day, at least for the initial grade. All right. After that, I will put the grades in the initial grades. Then, after that, I will still take those delta maths, but up until the end of this first term. All right. So what I'll do is at the end of the first term, I will go back and I'll regrade every single delta math that I gave you over the term. All right. So if you did it, it will be updated. But here's the catch. If you want that grade changed sooner, you need to email me or tell me, and I'll do it sooner. Otherwise, I'm not going to do it until the end of 6 weeks. All right? Does everyone understand that? And that's only for delta math. Paper assignments, I check the very next day. And if you're absent, you need to show it to me, or else it's going to be a 0. All right? So we've only had one paper assignment so far. That was the 1.2 stuff. So if you know you were absent when I checked 1.2, which I think was Monday, all right, you need to show me that ASAP. I haven't put the grade in yet, but I probably will within the next day or two.
What grades have they?
Nothing. Delta maths won't get graded till after the test, but I need to put the paper assignment in. I'll probably do that during my class today. All right.
Ms. Murphy,
Yes.
1.2 was pages 7 and 8.
Yes. Yes. All right. All your other assignments have been on delta math so far. And then don't forget, you're still responsible for your journals. It's mostly a copy job, but remember the examples specifically are the ones that you have to do. So the information you can copy, but the examples you have to do. And I did help you out. I went ahead and started the examples for you, so I graphed the original for you. But you have to graph the new and list the points for the new. That's basically what you're doing for all those goals. All right. Any questions? What's going on?
No, but can I wash my hands?
So, again, that's what's going to happen over the snow day. Besides that, you won't really get anything new because we should be finishing the unit by tomorrow. All right. Okay. So let's go ahead and hop on into symmetry very quickly. So go ahead and take out your packet, go to page 17. Now, symmetry is not really a transformation. It's more of a phenomenon that happens due to rigid motions and transformations. All right? So with symmetry, what's basically happening is it's saying that if we graphed a figure and if we did a specific type of transformation, so typically that's either a reflection or a rotation, depending on the angle measure that's being rotated or the line of reflection itself, symmetry happens when a figure maps onto itself. Meaning, if we did the transformation, it'll look like we didn't even do a transformation. It'll just be the exact same figure. Position, orientation, everything. All right? So it would look like, you know how on Delta Math, if you graph the same line, it just graphs over itself, it changes the color? That's what it'll look like. It'll look like it'll be just right on top of itself. All right. So, like I just said, symmetry is the ability to map an image onto itself. All right, so that shows that it has symmetry. So do you guys remember when, you were in elementary school and, you may have done an art project where you had to paint your hand, slap it on a piece of paper, fold it in half, and open it, and you get handprints on the other side? That's what I'm talking about with symmetry. All right. The two types is a line of symmetry and rotational symmetry. So, first, we have the line of symmetry. So if a figure has a line of symmetry, that means the figure can be mapped onto itself by a reflection. Now, there could be more than one line of symmetry on a figure. So the maximum lines of symmetry that a polygon can have is equal to the number of sides. The maximum is always found in a regular polygon because all sides and all angles are congruent. So when I say regular polygon, the best way I can say it is think about a square. What's true about a square?
It has 4 sides.
Four sides, all sides are equal. What else?
It's a quadrilateral.
It's a quadrilateral, it's 4 sides. What else?
It has lines that are parallel.
Yes, what else? What about the angles?
They're all 90.
They're all 90 degrees, so they're all congruent. So a square is what we call a regular quadrilateral. All right. Meaning that all the sides are congruent, all the angles are congruent. So in the quadrilateral world, a square is a regular quadrilateral. So for example, here they have a regular octagon and a regular pentagon. And all that means is that all these sides on the octagon are congruent and all the angles are congruent. All these sides of the pentagon are congruent and all the angles are congruent. All right, that's all regular polygon means. Means congruent sides, congruent angles. All right. So let's look at this first figure over here. So they're saying that its line of symmetry is right here. All right. So let's just say, just for fun, let's just say this is A, B, C, D, E, F, and G. Now, can someone tell me 2 points that look to be the same distance from that red line? That appear to be the same distance from that red line? C and F. All right, they appear to be the same distance. And remember, what's usually the strategy for reflecting something? What do we do when we reflect something over a line? We flip it, but how do we know where to flip it to? This is a review from earlier this week. I kind of just gave it to you. I said same distance. What do I mean by that?
Don't you take how far the point is from the line and then do it on the opposite side?
Right. You count how far away it is from the line and then do that same distance on the opposite side of the line. So, for example, let's say I was transforming C. All right. C has the same distance as F. So when we transfer it to the other side, C prime will map onto F. And vice versa. So F prime will map onto C. What other 2 points look to be the same distance? Someone besides Luke? B and G. All right. So B looks to be the same distance from the line as G. So that means B will become G prime and G will become B prime. Now, A will still be A prime because it's on the line. And I didn't give this point a name. Let's call that one H. And H still be H prime because it's on the line. What other 2 points look to be the same distance? D and E. So D is about the same from the line as E is. So D will become E prime and E will become D prime. So in other words, if we graph this figure, even though we did the reflection, it's still the exact same figure. All right, it didn't move. Because when we did reflections yesterday or earlier this week, when the reflections that we did, we would get a distinct different shape. All right, but here it didn't even look like we did anything. All right, that's what it means to have symmetry. When you finish the transformation, it doesn't even look like you did anything. All right. Now, with these regular polygons, since they're regular polygons, they have the same number of lines of symmetry as they do sides. So an octagon would have how many? 8. Pentagon would have how many? 5. Hexagon will have how many? Decagon will have how many? 10. Good. So decagon, decade, 10. All right. That one was just, I want to see if you knew what a decagon was. All right. So, for example, this octagon has 8 lines of symmetry. So here's one of them. So if I mapped each of these points, we would get the same figure. It won't move. Here's another one. Here. Here. So if I reflected over any of those colored lines, I would get the exact same figure. It would look exactly like the current octagon that you see now. It won't change orientation. It won't change location. All right. Same thing with this pentagon. All of these lines, but it only has 5 of them because it only has 5 sides. All of these lines, if I reflected over them, I would get the exact same pentagon orientation and all. All right. So let's do an example. So for this one, they want to know what line could we reflect triangle ABC on so that maps onto itself. So let's go ahead and graph this real quick. So I have -1, 3 to be A, 3, 6 to be B, and 7, 3 to be C. This is A, B, and C. So think about it for a minute. And remember, it's not the best drawn triangle to scale. Like, for example, this line isn't nicely straight, but imagine if it was. So, let me ask you this. What type of line do you think would work? Horizontal, vertical? Vertical, all right? So vertical line would work. So if I drew a vertical line somewhere and reflected it over, I would get the same line. I would get the same triangle. So someone besides Ephraim or Luke or Owen, those are my 3 high flyers right now. Which line or what value, either X or Y, would be that line of reflection? So where would I draw that vertical line? It would be on an X value. What X value? 3. Good. So at X equals 3, so go through that B value, we'll have a line of reflection. So right here would be my line of reflection. All right. And so let's test it. B will stay where it is. That'll be B prime. A is 1, 2, 3, 4 away. On the other side, be 1, 2, 3, 4 away. So C becomes A prime. and vice versa. So A becomes C prime. And we get the exact same figure when we did the reflection. So the line that we're looking at is y equals 3. That's the line of reflection. That would give us symmetry. Any questions on that so far? All right. So let's look at these pictures here. Now, there may or may not be lines of symmetry. So sometimes there is, sometimes there isn't. How many lines of symmetry do you think that this square has? 4. All right, so a square has 4 because remember, it's technically the regular version of a quadrilateral. So here's 1, 2, 3, and 4. Those are all the lines of symmetry. So a square has 4. The next is a parallelogram. First off, do you think it has a line of symmetry? It actually doesn't. All right, because anywhere I draw it, so for example, if I drew it here, if I flipped it over that line, this angle is bigger than this angle. So it wouldn't match up perfectly. If I drew it here, same thing. This angle's smaller than this angle, so it wouldn't match up perfectly. If I drew it in half, same thing. This angle's bigger than this angle, so it doesn't work. And same thing going this way. All right. So that one does not have a line of symmetry. So there's no line of symmetry. What about this last shape? Well, it's not, it's just a shape. Do you think it has a line of symmetry? No. Because it wouldn't be perfect. So if I flipped it here, this point would be right here. All right. If I flipped it here, this point would be here. All right. Same thing if I did diagonally, the points just won't line up. So that one also doesn't have a line of symmetry. Now, sometimes a figure may not have a line of symmetry, but it has rotational symmetry. So rotational symmetry is when we turn the figure and it looks exactly the same. So it's a center point rotated a number of degrees between 0 and 360, where the image is perfectly congruent to the pre-image. And we exclude 0 degrees and 360 degrees for obvious reasons, because obviously if you go a full circle all the way around, of course it's going to look like itself. All right. So the point of which we rotate around is called the center of rotation. And the angle that we turn around is called the angle of rotation. So I told you guys earlier on, mathematicians are pretty straightforward when they name things. They're not that creative. So whatever they name something is pretty much what it is. All right. Now, let's look at an example here. They said that this figure, so this star, has a rotational symmetry of 72 degrees. So if I rotate it in increments of 72 degrees, this star will look exactly as you see it. All right, the orientation won't change, and the shape itself won't move. Why do you think it would be 72 degrees? So let's say that I drew a circle around here. And it's not going to be the prettiest circle, but let's say I just drew the circle around here. There's 5 points. Okay? So if we want to map onto itself, let's say we were moving this point. If we go 72 degrees, it would end up here. Another 72 degrees here, so on and so forth. All right, it would look like the exact same triangle. But why does that play into the 72 degrees? Where does that 5 help us figure out 72 degrees?
Because if you do 72 times 5 equals 360.
Right. So if we do 72 times 5, it's 360. Or if we do 360 divided by 5, we get 72 degrees. And it's because there are 5 spots where it can rotate upon itself. So that's how we know it's 72 degrees. All right. So for any regular polygon, so remember that means same sides, congruent angles. If it has insides, so whatever number of sides it has, the polygon can be mapped back onto itself by a rotation of x degrees. And the way we find it is we just do 360 divided by the number of sides, and that gives us our angle of rotation. So, for example, if we took a regular pentagon and mapped it onto itself, what would be the angle of rotation, and what would be the order of symmetry? So before we get into that, the order of symmetry, I forgot to say what that was. Order of symmetry is the number of times the figure can rotate upon itself. So for example, up here, the order of symmetry would be 5 because it can rotate on itself 5 times in 5 different places. So for a pentagon, what do you think? So what would be the angle of rotation for a pentagon? First off, how many sides does a pentagon have? A pentagon. 5. So pentagon looks like this. It's not going to be a perfect pentagon, but so that's a pentagon. It's a regular pentagon. So even though it's not drawn to scale, all the sides are congruent, all the angles are congruent. So how many times can it map on itself? 5 times. All right. So like, let's say we start at this point. We can go 1, 2, 3, 4, 5 different spots and it'll map onto itself perfectly. So if the order of symmetry is equal to 5, what's the angle of rotation? 72. How'd you get it?
If we do 360 divided by 5.
360 divided by 5, 72 degrees. Any questions on that? All right. So now let's look at some examples. These are quick. All right. First shape, what is that? That's an octagon. Do you think it has rotational symmetry? Yes or no? Yeah, it does. How many points can it be rotated around and map onto itself? So what's the order of symmetry? 8. It says 8 sides. So what would the degree of rotation be? What's 360 divided by 8? Think about it this way. What's 360 divided by 4? Well, think about it. Coordinate grid will add up to 360. So 90 is divided by 4. Now half it again.
45.
45. What about the trapezoid next? Do you think it has rotational symmetry? No, it doesn't. What about this next one? Do you think it has rotational symmetry? It actually does. All right. But because if you rotate from here to here, it will map onto itself. All right. So it would map onto itself twice. So what would the degree of rotation be? 180. What about H? It would. So again, it would map onto itself twice. All right. Because you would have to go from here to here. And by that, I mean, like you'd have to rotate all the way over here. So it'd map onto itself twice. So what would the degree of rotation be? 180. All right, so that's symmetry. Any questions on that? All right. So before we move on to dilations, I'm going to give you guys a 3-minute break. If you need to use the restroom, you may, but you may not wander the halls, or if you just need to like lay your head down for a second, you can do that. But you need to be, if you do leave the room to go to the restroom, you need to be back in here in 3 minutes.
Yeah, I've seen neighbors in the past, so
So are you excited to meet today? Would you change your
I'm not coming on, unfortunately, I had to decline it.
Oh, that sucks.
Are you excited for it?
Yeah, hopefully we keep our undefeated streak. It's been nice.
New Jersey, oh, it's you have to take Spanish one.
I took Latin.
We need 2 consecutive languages.
All right, guys, head back to your seats. Break's over. All right, so back to the grind. Dilations is pretty short too. All right. So in your packet, go to page 21. All right. So heads up, guys. Come on, break's over. Heads up. So dilations. Dilations is the last type of transformation that we are going to talk about. Now, a dilation specifically is a transformation that moves each point of the original figure along a straight line drawn from a fixed point. It's called its center of dilation. And it must include what we call a scale factor or ratio to that center of dilation. So in layman's terms, all a dilation is that it makes your shape bigger or smaller. All right, depending on whatever the scale factor is. All right. So that being said, a dilation produces a figure with the same shape as the original, but not the same size. So what category of transformation does dilation violate? So every transformation that we have done up to this point has been a what?
Rigid motion.
A rigid motion. So a dilation violates what we know about rigid motion. Why does it violate that? It changes its size. So remember, rigid motion creates congruent figures. So same shape, same size. As soon as you change the size, it's no longer a rigid motion. All right? So it creates what we call a similar figure, which we'll talk more about in Unit 2, but not a congruent figure. Similar means same shape, but different size. Size, I should say. So dilations are our first type of non-rigid motion. And it's the only non-rigid motion transformation we will be talking about. Now, if the scale factor is greater than 1, so the scale factor, let's call it S, is greater than 1, it's called an expansion. And essentially, expansion is just a fancy word for it gets bigger. If the scale factor is less than 1, so in other words, it's a fraction. So if the scale factor is between.
Hey, I just ran into Miss Laura, so I let her know, because I was down there talking to Mr. Holt.
Okay, cool. Thanks.
Yep.
So the scale factor is between 0 and 1, so that means it's a fraction. It's what we call a compression, which is just a fancy word for it gets smaller. Yes?
What is that you wrote under scale factor is less than 1?
0 is less than S, which is less than 1. It just means between 0 and 1. So in layman's terms, that just means between 0 and 1, which any number between 0 and 1 is a fraction. Like a true fraction, like numerator smaller than denominator. All right. Now, some properties of dilations. All right. The image and pre-image are the same shape, but not the same size. The angles are still the same measure. Ratios of the corresponding line segments give the scale factor. So in other words, if we set up a proportion, so another name for that is proportional. So if we set up a proportion, like if we do one side divided by the other side, we should get the scale factor. The area increases by the scale factor squared. And the dilation, which does not pass through the center of dilation, travels parallel to the original image. So we should not pass through the center of dilation unless like our figure was originally on that center of dilation. All right. So here's some examples of dilation. So if the center point's here and we dilated, let's say this figure, it got bigger. This figure, all right, it got smaller than this figure. All right, that's what dilations look like. It's literally getting bigger or smaller. And the orientation should stay the same. It's just bigger or smaller. Now, center of dilation. Typically in this class, we'll do centers of dilation at the origin. So in this class, we focus solely on the center of dilation being at the origin. All right. So for that, all you do is just multiply the coordinates of the vertices of the original figure by the scale factor to get the new coordinates. So in other words, if you start with the point xy, you get kx times ky, where k is your scale factor. All right, so for example, let's just say that k was equal to 2. I would multiply whatever I get for xy times 2. So my new points would be 2x, 2y. All right, because I had to multiply the x and the y both by 2. Does that make sense? How scale factors work. Now, another way you can write a dilation, so this is the function rule, is a capital D, and then the scale factor will be in the subscript. It'll be like a little number. So again, for example, if k was 2, we would write it as d2. So capital D means dilation. The little number in the subscript, that's your scale factor. Any questions so far? All right, so let's actually do some practice with this. So this first exercise, they gave us A, B, and C. And they want us to follow this rule. So if we start with the points x, y, we should end up with 2x and 2y. So first off, what's my scale factor? So what's k equal to, your scale factor? 2. Because that's what we're multiplying to x and y. So your scale factor is whatever you're multiplying to x and y. So what we're going to do before we even graph this, I'm going to rewrite the coordinates that we have, which they already gave us. Now, how do you think I would get A prime? What would I have to do? So we're following this rule up here. So this rule up here is basically telling you what to do. So what do you need to do? Multiply 3 and 4 by 2. So we're going to do 2 times 3 and 2 times 4, which would give me what? 6, 8. So that's my A prime. So A prime would be at the point 6, 8. B prime, we would do the exact same thing. So we're multiplying the 4 and the negative 2 by 2. So I have 2 times 4, 2 times negative 2. So someone besides Ephraim, what's your new point? 8, negative 4. So B prime would be at 8, negative 4. C prime, same thing. Just multiply it by 2. So we're doing 2 times negative 2, 2 times negative 1. So what's my new point? Someone who has not talked yet. Negative 4 and negative 2. So right here. So my figure will look like this. Do you guys see how it's bigger than the original? If it's bigger and our scale factor was a number greater than 1, it should have gotten bigger. All right. Let's do another example. So I'm going to take a minute and graph this parallelogram using these 4 points. So I have 8, 10. So right here. 6, 6. So right here. 12, 6. And 14, 10. Here's my original figure, and it's the shape STUV. Now, it says we're multiplying by a scale factor of 1/2. All right. Now, multiplying by 1/2 is the same thing as doing what? Dividing by 2. All right. So basically, for each one of these numbers, we're going to divide it by 2. That's the same thing as multiplying by 1/2. All right. So S prime would look like 1/2 times 8, 1/2 times 10. So what's my new point? 4, 5. All right, so S prime would be at 4, 5. What about T? If I divide both of those by 2, what would I get? 3, 3. So that would be T prime. What about U? 6, 3, and then V, 7, 5. So my new figure would look like this. So I got 3, 3, 6, 3, and 7, 5. So that's T prime, U prime, and V prime. So our shape got smaller. Why did it get smaller? We were dividing, or we were multiplying by a number less than 1, or a fraction. Guys, do I even need to do the next example? It's just dilating by 2 again. So let's just get the new points. We're not going to graph it, but let's just get the new points. So if I'm multiplying by a scale factor of 2, means I'm multiplying all these points by 2. So A prime would be what? So I'm 6, 10. You're just multiplying these two numbers by 2. B prime would be what? 6, 6. C prime would be what? 10, 6. That's all you do. Whatever the scale factor is, that's what you multiply to the points. Pretty easy, right? That's all it is with dilations. All right. Now, the last thing is if a line segment AB is dilated using center point C, and it's not on AB, the scale factor of K, then the segment AB, A prime, B prime is equal to K times AB, and those two line segments are parallel. So what does that mean? All right. These two line segments would be parallel. This was the center. And let's say that AB was X in length. That means A prime, B prime would be KX if the scale factor was K. So let's see if we can locate for the image below. It says that MN and K is MN is the image of KL. So MN is the same thing as K prime, L prime. All right. So they want us to know where the center of dilation is. So we know that these two have to be parallel. So the center of dilation, we just take the other two sides and just connect them. So wherever they cross, that point is your center of dilation. We'll call it C. So all I did is, because these lines have to be parallel, all I did is just took the other two sides of the shape, continued the lines. Wherever they cross, that's the center of dilation. Now, how do you think I would get my scale factor K? So let's think about it this way. For example, let's say that I just gave you these points, but I didn't tell you what the scale factor was. How would you figure it out? So if I didn't tell you the scale factor was 2, but I gave you the original and the dilated points, how would you figure out what the scale factor was?
You divide A prime by prime.
Right. So in other words, you would divide, because remember, we're multiplying the scale factor to get the new point. So the opposite of multiplication is division. So you would divide the new by the original. So that's what you would do. So to get scale factor, you would divide the new by the original. So in this case, what's my new? Which line did they say is the new? or the image? It's highlighted, guys. MN is the image. Or so it's the new line. So I'm going to take the length of MN, so 12, and I'm going to divide it by what? 16. Now we know that that's not going to be a pretty number. So all we got to do is just simplify that fraction to get our scale factor. So what can I divide into both 12 and 16 to get a number? 4. So the simplified fraction would be what? 3 over 4. And that's equal to k. So what they did is that they multiplied 16 times 3/4 and they got 12. Now, let's take a minute and check that. All right. So if we check that, because I'm not worried about part C, because that's a math 3 thing. So we don't need this, because I don't care. But let's check that. So we're going to take 16 and multiply it by 3 over 4. So let's put that 16 over 1 so we have fractions. Who remembers how to multiply fractions? So we don't cross multiply. It's just straight across. All right. So if I do 16 times 3, that's 48 over 4. Because 1 times 4 is 4. And what's 48 divided by 4? 12. So we got what we transformed. So that's the way you can check yourself to make sure you have the correct scale factor. Multiply the original by your scale factor, see if you get the new. Any questions on dilation? All right, so now you should be able to finish that 1.4 delta math. And your new homework for tonight is just page 23. That's the part that's going to cover dilation. All right, so you guys got a solid 25 minutes. So you need to either be working on that delta math from yesterday or you need to be working on the paper homework, which I will check tomorrow, first thing. So page 23, I will check first thing tomorrow. All right? But you should have enough information to be able to finish the delta math. If you finish both early, work on your journal. Yeah. Go ahead.